Hello everyone. Today I am going to start the course about infinity Laplace equation. First of all, why it's important topic? Because this is real application in semi-supervising learning and machine learning. Therefore, this topic is one of very important topics nowadays. So everything's come from minimizing of this integral du square dx in the some domain omega, and this one is equivalent by using Lagrange equation. This is in course of calculus of variation. Using Lagrange, we come to this PDE. Divergence of du is equal to 0. Okay, this is Laplace equation. Now, how about minimizing this du not in the power 2 but power p dx? Again, when we use Lagrange, we comes to divergence of du p minus 2 du. But for now, it's not for us important how we comes from minimization of this problem to this. How we come using Lagrange equation, but you can learn it in chapter 6 or chapter 8 of Evans' book. So we will not discuss how from minimization integrals goes to PDE. Okay, it's another topic in PDE. Now we will start working with this PDE. This the P Laplace equation calls minus divergence of du p minus 2 times du is equal to 0. Let's look at when p is equal to 2. It will be like divergence du. It will be Laplacian is equal to 0. So it becomes Laplace equation, which we learn it in, I think, in the chapter 2 of Evans. So how about if du is equal to 0, we say that u is harmonic function. What does this mean? Ux plus uyy, for example, in 2 dimension, this one is equal to 0. Partial derivative of u in respect to x plus partial derivative in respect to y is equal to 0. So let's consider when p is greater than 2. So our du, when our du is equal to 0, so we get du p minus 2 is equal to 0. This one calls degenerate form. And when p is less than 2 greater than 1, du is equal to 0, and du p minus 2 goes to infinity. This case calls singular. Okay, and our focus will be when p is infinity, the infinity Laplace equation. So divergence of du p minus 2 du. When we open using the definition of divergence, we will get du p minus 2 times the divergence of du plus d times du p minus 2 times du. This one is equal to du p minus 2 Laplacian du Laplace of u plus p minus 2 du p minus 3 du divided by du times du square times du. Why it becomes like this? Because see, we are taking a derivative of this one inside this p minus 2, and the power will become minus 1, and again we have to take derivative of absolute value. It is absolute value of du divided by absolute value of du times again du. We have to take derivative of du and multiply by du. So we got p minus 2 du p minus 4 or p minus 4 and du square du and p minus 2 plus d square u du times du. Okay, just we opened, and now what we will do, we assume that divergence of du p minus 2 du, this one is equal to 0. This one is by definition of Lagrange, which is said above. So from here we get p minus 2 times du p minus 4 du square Laplacian u p minus 2 plus d square u du times du is equal to 0. So now we have to take limit when p goes to infinity, because we want to study when p is infinity, and so and also we assume that absolute value du is not equal to 0. So if this one is not 0, this one is infinity, then this one should be equal to 0. So we get that because p going to infinity, this part becomes 0. We got t square u du times du is equal to 0. And let's call this one as d infinity of u. What does mean this one? In other words, Laplacian infinity of u is equal to the sum e and g from 1 to n when we take derivative u respect xi and xg, uxi and uxg is equal to 0. This is the infinity Laplace equation. Okay. Yeah, if we are saying that we study this equation or we are trying to solve this equation, it doesn't mean we can solve it, because almost 90% of partial differential equations are unsolvable. We can just study some of properties. So let's, when is equal to write Laplacian infinity, it will become ux square plus ux y uy, again because it's symmetric, this is times 2 plus uy square. This is when n is equal to 2. So okay, for today it's enough, just about definition of infinity Laplace equation. Next lecture, inshallah, we start with Lipschitz extension problem.